Hello and welcome to the lectures on state space approach to control system analysis and design. This is the third lecture in the chapter on linear observers and the separation principle. And in the first one we discussed a full order observer. In the second one we discussed the reduced order observer. And now we are going to discuss the separation principle. What we said in both, while summarizing the full order observer as well as the reduced order observer, that it should be possible to use the observer states for control in place of the actual system states. Now through this one, through the discussion on separation principle, we will actually get convinced about that point. That point was postponed. Now let us proceed and see. So we had a controller design assuming accessibility of states for feedback. It was done independently without thinking about observer, and then we designed the observer to generate the estimate of state variables of the system, either the full order or the reduced order. Now these are the questions. Can the observer states be fed back in place of the system state to control the system? So we designed u equal to minus kx, and we want to use z here. So we want to implement u equal to minus kz. Now can it be done? Is it possible to feed back z in place of x? This question. Second question is, arises like this. Observer equation was something like, let me write here, z dot equal to az plus bu plus g y minus cz. Now of course this, assuming that this game of the observer has been designed, A and B are known. Now what we see that this u, which we wanted to bring through this u equal to minus kx, x is not known. So how u is known? And this equation requires the knowledge of u. So the observer implementation, how it is possible? The observer requires the knowledge of the input, and the input is dependent on the state variables of the system, which is unknown. X is not known, so how u is known? And if u is not known, then how the observer can be implemented? Both these questions, they are to be answered by the separation principle. That is the objective of the discussion. In particular, through the separation principle, we shall see that how the control law for full state feedback can be combined with the observer, and it will give a general control law in which all state variables are for the system for which not all state variables are accessible. For those systems, it will give a general control law. And we will see that the closed loop system comprising of system to be controlled and the controller possesses the same dynamics which is with the full state feedback and the observer. So dynamics of the closed loop system is of that with full state feedback and with the dynamics of the observer. These things we will see in particular through the separation principle. We proceed ahead. So the meaning of that statement is that the poles of the overall system, I mean the system comprising of the actual system in which the feedback is implemented of states of the observer. So that gives the overall system. The poles occur at the locations selected for the system to be controlled with the full state feedback. So those poles which occurred through full state feedback and the locations which were selected for the observer. So poles of the overall closed loop system comprise of the poles of the closed loop state feedback control system and the observer system. Of course, we have a very strong assumption that the design of observer is based on the exact dynamics of the plant. Of course, the control design was also based on the exact dynamics of the plant. So both for the controller design as well as the observer design, we assume the knowledge of exact plant dynamics, that A, B, C matrices and that state space model in which these matrices are used is assumed to characterize the system with full confidence, full faith. If, however, the system x dot equal to ax plus bu, that model is not a true representation of the given physical system, so then in that case means we have the inaccurate model. So what is the effect of inaccurate model and how to consider this? This is outside the scope of our discussion, but there must be some way to analyze, to find out the effect of the inaccurate model. There must be some way, in some manner this has to be factored into a practically useful design. We proceed ahead. We consider, as usual, the nth order system described by the standard state space equation. Here it is linear time invariant description, x dot equal to x plus bu, y equal to cx, x belonging to x of dimension n, u of dimension m, and y of dimension t. So we have n-dimensional state space, m-dimensional input and p-dimensional output. And this is the state diagram representing the system. Now what we are planning to do, we have this state feedback control designed. Okay. And the intent was, while designing, we assumed that the system state, which is here, will be tapped and fed through the gain that which is calculated by various ways and implemented. So this input u is minus kx plus this r, this one. So we designed the state feedback with the assumption that states will be available for feedback and the system closed loop will be implemented like this. This state will be tapped, it will be multiplied through the gain k, fed back at the input terminals. And this is of course the open loop system. If this was not done, then this is the open loop. Rest of the thing is representing the open loop system. So we designed the full state feedback control with that premise, that thing in the mind. However, we don't have the states for feedback. So we designed an observer. Now we will consider reduced order observer little later. Let us first consider with situation with the full order observer. We have this observer equation in which we have obtained a G, and we want to control the system by feeding Z in place of X. So it was u equal to minus kx. However, we want to implement this u equal to minus kz. So instead of x, we are using z. And at this point, we assume that probably it will work. So let us see whether or not it will work. So you saw that we were ought to pick up this one through this k. However, what we are doing, we have actually picked up this observer state z and we have brought it at the terminals where this was supposed to have gone through the gain k. So we are going to do this, and what will happen, that we have to see. So how the overall dynamics is, that we are going to see. See, we know that if it was fed here, the overall dynamics will be characterized by A minus Bk. And we know that this has some dynamics for which we designed the gain G here. But then when we have made the connection from here to K, then we have to actually see how it behaves. So we have to see in the dynamics of the overall system, which comprises of the open loop system and the observer, which is of the order 2n, and the feedback of estimated state. So when we have the feedback of the estimated state, the system is x dot is ax minus bk. See, it would have been x, but now we are forcing it to be z. That closed loop system with the state feedback was x dot equal to ax plus bu, and that becomes b into minus kx. This is something which was supposed to be, but what we have in place of x, we are using z. So we have x dot equal to a minus bk, ax minus bk z, and the observer is z dot is az minus bkz plus g cx minus cz. Now from where this is coming? This is coming because the observer equation was that z dot is az, z dot is az plus bu plus g y minus cx. So in that we are doing the substitutions. So we get z dot is az, that u plus ax plus bu, az plus bu was there, so u is kz minus kz, so that bu becomes minus bkz, and this is y minus cz, y is cx, so g cx minus cz. This is the observer, and we had defined error e as x minus z. From this we will have z equal to x minus e, and therefore this equation becomes this, x dot is ax minus bk, in place of z we have x minus e. So we get a minus bkx plus bke. Rearrangement of term yields this, x dot as a minus bkx plus bke. And that means this e dot, which is x dot minus z dot, in place of that we can substitute x dot from here, this one, a x minus z minus gc x minus z. So we are just subtracting this x dot minus z dot. So a x minus z, ax minus az, that gives ax minus z, and this bkz minus bkz, that cancels, and this remains of course the minus sign. So we get E dot as x dot minus z dot, which is a x minus z minus gc x minus z, and x minus z is E, so this is ae and this is gce, and together it becomes a minus gc into e. So we have two equations for the overall system. One equation is this, x dot equal to a minus bkx plus bke, and other one is this, E dot is a minus gce. So basically we had the equation in terms of the system and the observer. It is in a way transformation. So the new coordinates are x and e. So x dot is given by this and e dot is given by this. The same system transformed in these coordinates x and e instead of x and z. And if we write these transformed system equations together, we have this, x dot, e dot, x dot was a minus bkx, a minus bkx plus bke, so this gives the first row, a minus bkx plus bke, and e dot was a minus gce, so e dot is 0 times x plus a minus gc. Now we find that in this form the equation has a very nice look. It is upper triangular. So that makes us simple to think that eigenvalues of the overall system are the eigenvalues of a minus bk, which is the closed loop state feedback system, and the eigenvalues of a minus gc, which is the eigenvalues of the observer. For those who cannot pick up this point, for them we can do a small bit of calculation that this matrix Si minus this matrix will give S minus A minus Bk minus Bk 0 and Si minus A minus Gc. And so the characteristic polynomial of this system will be obtained by taking its determinant, and that becomes determinant of Si minus A minus Bk into the determinant of Si minus A minus Gc. Because this is upper triangular, so it gets this form, and that is why if this has to be 0, this has to be 0 and this has to be 0 separately, and this 0 gives the eigenvalues of A minus Bk, and this 0 gives the eigenvalues of A minus Gc. And eigenvalues of A minus Bk means the poles of the closed loop system with state feedback, and eigenvalues of A minus Gc means poles of the observer with the gain G. So this is what is mentioned here, that the eigenvalues of the overall system are the eigenvalues of the closed loop system with the state feedback and the eigenvalues of the observer. This we have established mathematically. So the overall system design can be carried out following these two steps. In the first step, we can design a control law equal to kx under the assumption that all the state variables are accessible, minus kx. That we did. And design an observer to estimate the state of the system for which control law is designed in the previous system. This also we did. So earlier we did it intuitively, however now it is understood that we can indeed design the state feedback independent of the observer system, and observer is designed independent of the controller design. That can be done. This is established by this mathematical analysis. And then these two designs can be combined together to get the full state feedback control law with the observer. And we can indeed use Z in place of X. This we have now established mathematically. Now we want to establish the same thing in case of the reduced order observer. So with the reduced order observer, we have these equations. System model as before is this. However, it is expressed into this partitioned form. The state X is assumed to contain the two groups of states. One group is X1 and one group is X2, and each one separately characterized like this. And the output we said it only comprised of X1, C1 X1. So this is the from where we actually carried out the design of the reduced order observer. We have this observer model. The observer was characterized by this equation: xi dot is d xi plus ey plus fu. And in this we had established d equal to this, e equal to this, and f equal to this. We actually established through derivations. And then we said that Z1 is same as X1 and Z2 is xi plus Ly, and because y is C1 X1, Z2 is LC1 X1 plus xi. Z2 was Ly plus xi, and in place of y we substitute C1 X1 to get this. And the estimation error was defined as the difference of actual system state X2 minus the observer state Z2. Now we have to again establish the properties of the overall system consisting of the system with state feedback, in which the state we want to substitute by the estimated state through the observer. So of course we had seen that xi dot the estimation error epsilon dot was derived as this, and because this was to be 0, this was to be 0, this was to be 0 separately, we are only left with xi dot equal to d xi, which is here. And I was telling that now instead of feeding back this X through gain K1 through gain K here, now we are feeding the states of the observer like what is shown here in this diagram. So we have the states Z1, which is same as C1 inverse Y. This is Y here. So xt times C times xt gives Y, and that comes out of the system. So we multiplied with C inverse, C1 inverse to get Z1. That we are multiplying with K1, and then this Z2, which is Ly, this is Y and Ly comes here, this is Ly plus xi is Z2, that multiplying through K2 added to this K1 Z1, this K2 Z2, and that sum is being fed back here. So U equal to Kx, instead of that, because X is X1, X2, estimate of X1 is Z1, in fact it is same as X1, and estimate of X2 is Z2. So we are feeding K1, K2 into Z1, Z2. And we are interested in analyzing the overall system behavior. This is shown in this diagram, and this is also shown here through these equations, this one. So input is now being generated like this: K1 times Z1, K2 times Z2. And now because Z1 is exactly equal to X1, we do that substitution. But Z2, because this epsilon is X2 minus Z2, so we can substitute in place of Z2 X2 minus epsilon, which is here. So we get the input generated like this: K1 X1, K2 X2, and K2 epsilon. This is that through the error. As long as Z2 is not equal to X2, this K2 times epsilon will be non-zero. So with this relation in hand, the first equation of the system. So we had, let me see where it was little back here. X1 dot is A11 X1 plus A12 X2 plus B1 U. This modifies as X1 dot is A11 X1 plus A12 X2 plus B1 into U is this. So B1 into K1 X1, K2 X2 we keep here, and K2 epsilon we keep here. So B1 into K2 epsilon. In the same manner, the X2 dot is A21 X1 plus A22 X2 plus B2U, that B2U gives this one. B2 times K1 X1, K2 X2, this here, and K2 epsilon here. So this is what the system equation becomes. And when we arrange them in the matrix form, X1, X2 together, and this epsilon separately, the error separately, when we arrange them, we see that first equation, this one gives the first row here, this row, that second one gives the second row here, and xi dot is, we had seen in this side, xi dot is d xi, this one. So this is written here, xi dot is 0 times x1 plus 0 times x2 plus d xi. Sorry, epsilon dot is 0 times x1 plus 0 times x2 plus d epsilon. And this is a minus bk, so it is written here, and this is bk2, it is written here, and this one together is written as here 0, and this d is written here. Now again, this system is upper triangular. We can see this system is again upper triangular. This a minus bk, d, bk2, but this is 0. So again, the eigenvalues of the system, overall system, is the eigenvalues of state feedback system a minus bk, and the eigenvalues of the reduced order observer characterized by the matrix D. So again we see with the reduced order observer the same thing which we had got with the full order observer, that the eigenvalues of overall system are the eigenvalues of closed loop state feedback system and the eigenvalues of the observer. This we have established. So again we see that the implementation can be done. The two can be separately designed, that steps which we had shown for the full order observer, the same thing are here. We can first design a state feedback for the system, and then we can design a reduced order observer for estimation of only those few states which are not accessible. We can combine the two designs and we get the overall system. Same thing was there for full order observer, same thing for the reduced order observer. Now we see, because there can always be a deviation of observer system states from the actual system states, because the error will go to zero only asymptotically. That may take some time, smaller or longer. So how is the behavior of the overall system? This we are going to analyze. And we are going to do it full order observer. The same thing will hold good for the reduced order observer, or one can do to convince himself or herself. They can do themselves. So we had this equation for the state, and this was the equation for the error. In fact, this was the triangular system where we concluded the eigenvalues of the overall system. So these equations were derived, we had seen, and we assume that system is not having the equilibrium. The system is having a non-zero initial condition x0, and also the observer states are not fully converged, so the error is non-zero. We are assuming that both the initial conditions are x0 not equal to 0 and e0 not equal to 0. We are assuming this. So we take the Laplace transform of both these equations and we do some arrangement of the terms. So this, when we take Laplace transform of this, it will give s xs minus x0 equal to a minus bk xs plus bk es, and similarly this one. So first we rearrange this. We take the terms of xs on the left side and x0 on the right. So this one will give this first equation, si minus a minus bk, whole thing multiplying to xs equal to bg es plus x0. And we take Laplace transform of this and rearrange the terms. We get this one, si minus a minus gc es equal to e0. We get these things. And now in place of es, we obtain es from this and we substitute here. So the first equation gives this. Xs is si minus a minus bk inverse into bg into this into e0. It comes from here. Xs is this inverse into bg es, and es is this inverse into e0. So this is what comes here. This should be inverse here. And similarly this inverse into x0. This es will be this inverse into e0. So there was a typographical, so this should be inverse here. So xs is given by this. It consists of two terms, one with x0 and one with e0. So if we take inverse Laplace transform to obtain xt, it will be inverse Laplace transform of this term, this whole term, and inverse Laplace transform of this term. So we see that xt consists of two terms. One term depending on x0, which is very usual. The response of the system, we did solution of state equations, and we saw that the response of the system consists of two terms, one dependent on the initial state and other dependent on the applied input. Here there is no input, so it is very natural that the response of the system will consist of one term depending upon the initial state. However, what we notice that in addition to that, it contains a term which is dependent on this E0, the deviation of the initial state of observer from the actual system. That E is basically x minus z, if you recall, and so E0 is x0 minus z0. So if z0 was not equal to x0, we will have the time response which will deviate from only pure response because of the initial condition of state x. And that is the point. So overall system consists of a term dependent on x0 as well as a term dependent on E0 or x0 minus z0. So overall system behavior will deviate depending upon the initial deviation of state of the observer from the state of the actual system. Now we can see this through one simulation. This is the system for which we had considered the design of a reduced order observer. We take that system. Now this system, its eigenvalues are 0, minus 0.133 and minus 6.167. You can determine, see that you also get the same answer. For this system, we verify if we assemble the controllability matrix, we will have this controllability matrix, B, A, B, A square B will come like this, and the rank you will see 3. This Q is actually this one, Q is script Q. Rank will come 3. So that means the system is controllable. Similarly, if you assemble the observability matrix and see its rank, you will get 3. So both together means the system is controllable as well as observable. Means we can design a controller and we can also design one observer for the system. Controllability and observability properties are established for this system. So we first design a controller, say by using LQR. One can use pole placement also, but here in this example, using this Q and R in the quadratic performance index, X transpose QX plus U transpose RU dt 0 to infinity. If we design a controller, we get K equal to this. And the eigenvalues of closed loop system A minus BK will come this. One can verify. And of course the eigenvalues of open loop system were given in the slide here. They were this. So we have designed a closed loop system such that all the eigenvalues are very clearly in the open left half S plane. Even though this design was done using LQR, it got ensured. And we also design a full order observer for the system to have the observer poles at these locations. And thus we get the observer gains G as this. You can do the design and check, cross check that you get this G. And now we are going to analyze the overall system behavior, in which instead of state feedback, the feedback will be that of the observer states, and the state feedback system gain will be used along with the observer states. So we consider the typical 4 types of situations. The first one is, I had spoken about it earlier, that for that system this is the equilibrium. x10 is to be arbitrarily chosen, and x20 and x30 come from x10. So this is the equilibrium of the system 1, 20, 20 with the input 0. With 0 input, this is the equilibrium. And observer initial conditions, we assume 2 scenarios. In one scenario, the observer initial condition will be only slightly different from the system initial condition. And in another scenario, that will be significantly different, large difference, large deviation of observer states from the actual system states. Then we will not consider any application of external input and feedback of actual states. So this is one scenario. Other scenarios will be all other things like this. However, in place of actual states for feedback, we will feed the observer states, just to see how the two situations differ from each other. The third simulation is, the system is again at equilibrium, given like this one, and observer initial conditions very slightly different from this. And also we will now apply step input at t equal to 15 seconds, sometime later, not at t equal to 0. And we will give feedback of actual states of the system. So this condition differs from this condition. Here there was no input, here there is input, unit step input. And the fourth scenario is, observer states will be used instead of actual state. All other things will be similar to this one. So we are going to see one by one how the system behavior is in all these different scenarios. First one first. So this is the system state at the equilibrium. It is 1, 20, 20. Z0, if it was 1, 20, 20, then it would have been exactly equal to the initial state of the system, but we are assuming a minor deviation. So Z1 is not 1 but 0.75, 0.25 different from that. Z2 is not 20 but 15, and Z3 is not 20 but 25. No external input and actual states of the system are being fed back. So, because the system is at equilibrium, no external input is applied. What we see that the system states x1, x2 and x3, they will remain at equilibrium. No disturbance, no external input. So system states are at equilibrium. They will remain like this. However, observer states were not at equilibrium. So what we see that even though x1 is constant shown by the continuous line, z1, which is shown by the dashed line, undergoes some variations because of that initial difference in state. However, it stabilizes, it asymptotically approaches x1 in some time after 10 seconds, before 15 seconds. It has actually started matching the state x1. Similar happens to x2, z2 and z3. x2 and x3, they were at equilibrium and they remain at equilibrium. The two graphs are overlapping each other. Magenta and blue graphs are overlapping each other here. However, the estimate of x2, which is z2, is shown by the blue dashed line. It undergoes initial transient and stabilizes, catches up with x2 in a asymptotic manner. And z3, which is the estimate of x3, that also undergoes initial variations but catches up. So, in the absence of any external input, and if the deviation of observer states is small from the system states, we see that observer states, they asymptotically approach the system states. That was the intent of the design, it happens. Now, will the same thing happen in different scenario? That is done by this simulation. System is again at steady state, equilibrium. However, the observer states, they are much different. They are 0, 0, 0. They are much different from the system states. Again, there is no external input and still the feedback of actual state. So, all other scenes are identical to the first simulation, but there is a large deviation of observer states from the actual system states. So, as expected, x1, x2 and x3, they are steady at their equilibrium values, no transient. How the observer states behave, that is the point to be seen. So, we see that the first state of the observer, first state variable z1, it starts from 0, but after some time it starts overlapping with x1, it becomes almost same as x1, and so become z2 and z3. They become equal to x2 and x3 respectively. What is important to see that this observer states, they become asymptotic to the system states to the perception of human eye somewhere, let us say, between 10 and 15 seconds. The same was the situation, just I go back to show that even when the deviation was small at t equal to 0, the same was the situation. They approached to the actual system state and became asymptotic in about the same time. So, it's not the initial deviation that matters, it's the observer design that matters. Where the observer poles were put, that characterizes how much time it will take for the observer state to become asymptotic to the actual state, or in other words, the error to become asymptotically 0, the estimation error to become asymptotically 0. Now we see the third simulation. Initial condition of the system is such that the system is at equilibrium. The observer states differing only slightly from the actual system state. External input is still not applied. However, instead of actual states, we are now feeding back the observer states. And because the observer states are not matching to the actual system state, because there is one initial error, and in the analysis some time back we found that the response of the system will consist of two terms, one of its own initial condition and one depending upon the initial error. We see that reflects in the simulation. We see that x1, which was constant, if we are feeding x1 for control, is now showing some variations, initial variations, because we are using observer states for feedback and observer states are not same as the actual system states. So x1 undergoes initial variation, also x2 and x3 undergo initial variations. That happens. We see what happens to the estimated states. So we are showing x1, x2 and x3 and also on the same graphs z1, z2 and z3. So this is the graph showing x1 and z1. We see that even though x1 undergoes variation because we are feeding back the observer states, z1 starts approaching x1 as it was doing in the previous simulations, and x2 and z2 and z3 also start approaching x2 and x3, and the time taken is of the similar order. Again, it is a matter of where the observer poles were placed. We go to the fourth simulation. Everything identical to previous one, but now the deviation is large. And of course, the result of large deviation is that the initial transient which system experiences, actual system experiences and reflected through the behavior of x1 versus time and x2 and x3 versus time is that they are large variations. This scale to which the variations occur, they are large. You can go back and see. Here it was small within between 0.5 and 1 to below 1.5. Here it is above 2 and approaching well above -1. And similarly here. So if there is a large error, there is large initial transient, very obvious, but it is better to be convinced through simulations that happens. And the estimated states Z1, Z2 and Z3, they start tracking the actual system states after some time. So irrespective of how much was the difference, whether we were using actual system states for control or observer system states for control, this behavior is identical, that the estimated states become asymptotic to actual states in the time depending upon the observer design, where the poles of the observers were placed. It happens. Now we come to yet another simulation. Here the observer states are very close to the system states. You can see the first one matches. The second and third one are only very little different. And we give some time for system to stabilize. We don't apply input right at t equal to 0, but we apply input at t equal to 15 seconds. When probably the system will undergo initial transient and initial transients will start disappearing. That time we apply the input and feedback of actual state first, observer state we will see subsequently. So because x1, x2, x3 they are at equilibrium, they remain so, no initial variation is seen, and whatever variation is seen is in response to the unit step input at t equal to 15 seconds. That is reflecting in behavior of x1, x2 and x3. Observer states Z1 is exactly equal to x1. It is always tracing the same. The two values are actually coincident at all the instants of time. And Z2 and Z3 they undergo initial small variation, of course, but again they stabilize little before the 15-second time that we see that happens. So by the time the step input is applied, the states have converged. X2 and X3 have become, Z2 and Z3 have become asymptotic to X2 and X3. And then the system starts undergoing transients. The input was applied at t equal to 15 seconds. And we see that literally, not literally, to the human eye perception, there is hardly any difference between X2 and Z2 and between X3 and Z3. They are almost the same. So irrespective of whether the system has been applied some input or whether the system, no input was applied to the system, the observer states, they had become asymptotic to actual system state and they actually match to the actual system states. Next simulation, same initial condition, but now the feedback is of observer state. So here we see that because initial there was deviation between x and z, so the system undergoes initial transient expected, and it does. But they stabilize well before the application of the input at t equal to 15 seconds. And then the rest of the transient is in response to the applied input, step input. So x1 will go this behavior, x2 and x3 will do this behavior. Now what you notice, this is through the feedback of observer state. We had done the same simulation with the feedback of actual system state. Let us go back and see those graphs. Feedback of actual system state, you see, concentrate on these. It undergoes a peak which is between slightly above 1.1 and the time is slightly after t equal to 15. This is with the actual state feedback. We see what happened when we applied the observer state feedback. To the perception of human eye, you will hardly see any difference, and actually there is no difference whether we use observer state, because the observer state had already become asymptotic to the actual system state. So both x1 through the feedback of observer state or through feedback of actual system state and x2 and x3, they match. The behavior is exactly identical as shown from the simulations. That is the beauty. The observer states, see, during the transient there is no perceptible difference between Z2 and X2 and Z3 and X3. They match. So the observer states have matched. Once they have become asymptotic, they match. So the lesson to take from this simulation is that if there is some initial deviation, it will die down as long as we have designed the observer for stability, and subsequent response with the feedback of observer state will be same as the feedback of actual system state. This is what these simulations established by the numerical exam. Let us now summarize this lesson by making a few concluding remarks. Separation principle has helped us to establish that state feedback control and observer can be separately designed. The observer states can be made to approach the actual state fast by appropriate design. So if I said some in one of the preceding lectures, let me repeat, that the observer poles can be placed comparatively far to the left than the system states with the state feedback. So closed loop state feedback system eigenvalues, they are somewhere in the left half S-plane. The observer eigenvalues can be made further to the left of that. Of course, that will require large observer gains, but that may not be a problem because it is a simulation. It is not the actual system, but it is a model of the system. Okay. So by placing the observer poles very far to the left, we can actually make the states of the observer approach the states of the actual system quite fast. That is possible. And the overall closed loop system behavior with the feedback of observer state will be similar. We saw by analysis and we saw by simulations. Similar to that with full state feedback once the observer state converges to the actual state, allowing for some time for the initial deviation to decay. Then it will hold good. Now, there are some negative remarks. The observer state will exactly match the actual state, ideally only at t equal to infinity and in noise-free environment. We have to be careful that we can make the system the observer state to become asymptotic to the actual state, but in theoretical sense it can never match, it is only asymptotic. And then presence of noise in a practical system is something that cannot be ignored. However, all this treatment, entire observer design, separation principle, everything doesn't consider the presence of the noise. The observer design, like the state feedback design, required the exact knowledge of the system, mathematical model. So is the case with the observer design. Exact mathematical model of the system is required to be known. If the model is not known, because in practice it may not be the case due to a few factors. One is that physics of the system may not be fully understood. It may be only understood with some limitations. There could be poor understanding of the physics of the system. Or the other thing is that the exact dynamical model, even though it is known, it is so complex that it is not conducive to controller and observer design, and we are forced to resort to simplify the model. So simplified model will never represent the actual system to that much faithfulness as does a good exact model. So that limitation will be there. Other thing is that the system characteristics may vary with time owing to factors like aging, wear and tear and aging that may happen, and so the system undergoes unknown variations with time. And the design is some nominal model of the system. So there ought to be some differences. So effect of that is that the actual system behavior or the performance of the actual system will be somewhat different from the expected behavior or the performance established from analysis. There has to be always some difference, and we have to keep this in mind. So in summary of all this, we have to remember that these all the controller design and observer design, all these are based around a mathematical model which represents the characteristics of a system with limited faithfulness, limited fidelity. And we have to see from extensive nonlinear simulations and extensive simulations from as far as possible from the original complicated model that the overall system behavior is as intended. We have to keep these things in mind. Thank you very much. That brings us to the end of this topic, observer, linear observers and separation principle. See you again in a different lecture. Thank you very much.